So today our topic is Fatou's lemma. Very important. Okay, Fatou's lemma. But before stating or proving this theorem, what we are gonna do, we are gonna actually talk about lim inf and lim sup. So lim inf and lim sup, particularly lim inf. So if we have any sequence, so let AK be a sequence of real numbers, then we can define so B1, which is infimum of A1, A2 up to so on, and B2 is infimum of now A2, A3 up to so on. So this means that we can say that Bn is infimum of k is greater than n AK. So what do you think about the relation among B1, B2 and Bn? So if we take the infimum of A1, A2 and then we take the infimum of A2, A3, we delete the first one. So definitely then clearly B1 will be less than or equal to B2 is less than or equal to B3 up to so on. That kind of relation we have. Now if I ask you what if I take the limit n approaches to infinity Bn, so that will be actually limit n approaches to infinity and Bn is nothing but this is infimum of k is greater than or equal to NAK, and that is nothing but actually we say that sup of n and infimum of k is greater than or equal to NAK. Okay, so this means that what is lim inf is actually it is the sup of the infimum of the sequence AK. So and similarly what is if I say C1, then I will say take the supremum now. So instead of now infimum, what we are gonna do, first we have any sequence, so C1 is supremum of A1, A2 up to so on, and C2 is supremum of A2, A3 up to so on. So this means that Cn is supremum of k is greater than or equal to n AK. So now what kind of relationship among C1, C2 and Cn have? So the relationship is kind of so if we take the supremum of the set and then we delete an element from that set, so definitely if the sup is the biggest value and the biggest value we delete, so definitely in the next set the sup will be minimum value. So definitely so C1 will be greater than C2 is greater than C3 up to so on. Now if I take the limit n approaches to infinity Cn, this is nothing but this is limit n approaches to infinity and Cn is supremum of k is greater than or equal to NAK, and this is nothing but this is actually infimum of n supremum of k is greater than NAK. So you see what kind of relationship. So lim sup is the infimum of supremum and lim inf is the supremum of infimum. Okay, so now based on lim inf we are gonna actually state Fatou's lemma. So Fatou's lemma says let X as mu be a measure space and let Fn be a sequence of non-negative measurable functions on X. Then so lim n approaches to infinity, okay, inf lim_inf, okay, fn of x d mu is less than or equal to lim n approaches to infinity infimum lim_inf fn of x d mu. Sometimes I will just forget about the x, so we will just write fn, so don't worry. Okay, so proof. What we need to do, actually we need to apply MCT, because we have a tool that we can use. But what MCT says that you need to come up with a sequence of non-negative measurable function, an increasing sequence of non-negative measurable function. So since we know about lim_inf, so lim_inf is the sup_inf, so we can say that let gn is the infimum k is greater than or equal to n and fk. Then what we know then, so since inf, so 0 is less than g is less than equal to g2 is less than or equal to g3. So now we have, this is an increasing sequence, okay. So now if an increasing sequence, we can just go ahead and use MCT. So then, so by MCT, okay, so by MCT what we have, so MCT says that limit n approaches to infinity gn d mu is actually limit n approaches to infinity gn d mu. But what is the limit of gn? This is nothing but this is called lim_inf of fn d mu, and this is actually limit n approaches to infinity gn d mu. But what we need to know, that this side, which is this thing, is less than or equal to lim_inf of fn. So we need to somehow now do something with this term. So it is very easy to see that. So we can say that for all n, what we can, since gn is the infimum, so gn is always less than or fn. Thus we can use that gn d mu is less than or equal to fn d mu. Okay, order property, integral order property. But what we can say about limit n approaches to infinity gn d mu, this is actually limit infimum n approaches to infinity gn d mu. But since gn d mu is less than fn d mu, so this will be less than or equal to limit n approaches to infinity infimum and fn d mu. Thus what we got actually that, hence thus we are done with the proof that limit n approaches to infinity fn of x d mu is less than or equal to limit n approaches to infinity infimum and fn of x d mu. Hence we are done. So there's what we call Fatou's lemma. Okay, and thank